Ladies and gentlemen, girls and boys, I'm Alan Willison, and it's my privilege and pleasure to welcome you to this meeting of the Hertford Astronomy Group. The format of the evening is that we've got Martin who's going to be giving us a talk about the night sky with some lovely images to share with us. After that, he's going to pass back to myself, and I will then pass over to Dennis, who's going to introduce tonight's speaker. After the talk, there will be an opportunity to ask questions. For those of you at the university, you can ask them live, but please give the operators a chance to get a microphone to you so that the people on Zoom can hear what the questions are. For those of you on Zoom, if you could use the chat facility to send your questions over, then we can make sure that they are read out and answered. So it's my pleasure to hand you over to Martin, who's going to talk about the night sky. So over to you, Martin.
Thank you, Alan. I'm just going to share my screen. Can everybody see that okay? Great. Okay, so just going to talk about this little snippet I found on the internet the other day. I thought it was quite interesting. It's nice to know that Hubble is still doing a major bit of work out there, even though the James Webb Telescope is proving to be a fantastic tool. It's nice to know we're still getting great images from Hubble. So this is about a group of astronomers actually in, I think, Sheffield. So I'll quickly read through this. So NASA's Hubble Space Telescope has recorded a record-breaking discovery of a massive cluster of stars located in a galaxy approximately 50 million light years away from the Earth. The cluster is named R136. It's the most massive young cluster of stars ever discovered, with a total mass of around 450,000 times that of our Sun. The discovery was made by a team of astronomers led by Paul Crowther of the University of Sheffield in the UK, who used Hubble's advanced camera for surveys to observe the cluster. The researchers were able to identify over 800 stars in the cluster, many which are among the most massive and luminous stars ever discovered. R136 is located in the Tarantula Nebula, a massive star-forming region within the large Magellanic Cloud, a satellite galaxy of the Milky Way. The nebula is so large that it's visible to the naked eye from the Earth and appears as a fuzzy patch in the southern hemisphere. Unfortunately, we can't see it here in the northern hemisphere. So well done, Hubble. Well done, Sheffield, for that new discovery. Move on. So I'm going to move. I was going to do some work with Stellarium tonight, but I decided to just do a few images on here instead. So interesting thing here is about something we're calling the red triangle. As Mars moves into the same area of space where Aldebaran and Betelgeuse, they've named this the red triangle. So for obvious reasons, Mars appears very red in its color, and if Aldebaran in Taurus is the eye of the bull, is very red, and Betelgeuse in Orion is a red giant. So I've got on that drawing there, 5th of March is how it appears, and Mars is slowly moving towards Gemini, so it's actually stretching by the 26th of March. But it'd be worth, if you get a clear night, go out and have a look at those. They are very red, and they are quite beautiful to watch. So I put a little bit of blurbs there, which really just reflects what I've just said. Okay, so another thing worth looking at, especially if you own a pair of binoculars, is the Beehive cluster. Now, this is not far from that bit of space we were talking about. It's a little bit further east, but in the constellation of Cancer. So on Friday the 10th, if we get a clear night, just before moonrise, the Beehive cluster is close to its highest point in the sky. So that's one good way of finding it. And it's perfect for looking at through a pair of binoculars. So the recommended size here is 10 by 50. The reason for that is that you can hold them fairly steady, and anything bigger than that, you tend to get, it's very difficult to hold unless you've got them on a stand or a tripod. So that refers to the size of the lenses and the magnification. So the lenses are 10 centimeters, sorry, and magnification is times 50. So there's a little bit of information about the Beehive cluster there. It's an open star cluster located in the constellation of Cancer. It's approximately 600 light years from Earth. The cluster is known as M44, as its designation by Charles Messier. It's relatively young, estimated about 600 million years, which is baby time in astronomical terms, and hosting about 1,000 stars. I have looked at this cluster myself, and it is how it appears on the screen here. It's got lots of beautiful gold, red, blue, and white stars, and it's quite a lovely thing to look at. Moving on, I was out last night when we had a bit of a clear sky for a while before the clouds zoomed in, and pleased to see Venus and Jupiter still very prominent in the western sky as the sun was going down. Definitely worth viewing them together. It makes you realise just how bright Venus is when they're together like that, because Jupiter on its own normally is a very bright planet, but Venus completely outshines it, but it is a lot closer to us. And the atmosphere of Venus being mainly gas, it gives it a very high albedo, a reflective ability. So a lot of the sun's light is reflected back. Okay, so moving on to the vernal equinox, which is only a week or so away. The equinox is when we get equal day and night. So I've put a bit of information for those who may not understand mathematics on it. On Monday, the March the 20th, 5:24 EDT, which is American time, but it's 21:24 GMT. Sun will cross the celestial equator, traveling north, marking the vernal equinox in the northern hemisphere and the beginning of the northern spring. Days and nights will be equal on that day, and the sun will rise due east and set due west, as it always does. At mid northern latitudes on the March equinox, the amount of daylight added up each day reaches a maximum of 3 minutes. So another little thing to look out for coming up is the moon, a crescent moon, very close to the Pleiades. The Pleiades are a beautiful, very tiny, small cluster of stars, but very bright. Also known as the Seven Sisters. So I'll just read out what we've got on here. There's some interesting information. Once the sky darkens on Saturday evening, March 25th, the bright little cluster of stars named the Pleiades, the Seven Sisters, also known as Messier's 45, will sparkle about 2 fingers width to the right of the waxing crescent moon. By the time they set around midnight, the moon will have shifted to the left of the cluster. To better see the cluster of stars, hide the moon beyond the edge of your binoculars field of view. A large aperture telescope and a long exposure photos can reveal faint blue nebulosity around the cluster's brightest stars. In Greek mythology, the stars are named after the daughters of Atlas, Pleione. Okay, so I'll talk a little bit about Sirius, also known as the Dog Star. The reason it's called the Dog Star, it's in a constellation Canis Major, which means large dog, basically. So and Sirius is a part of the dog. I think it's in the neck of the dog, actually. But if you look at it on the constellation lines, it sits where the head joins onto the top of the shoulders of the dog. So the interesting thing about this particular drawing is that it's got also Orion's belt in here, and the sword, and I was talking about Betelgeuse earlier on, which is there, and also Procyon, which is there, just to the left, making a triangle there. So March is a great month to marvel at Sirius. You can only see it at this sort of time of the year because it's quite low down. It's just out of sight. It's the sky's brightest star at night because it's the brightest star in the constellation of Canis Major. Sirius is super easy to locate. Just face towards the south and look for Orion. The three bright stars that make up Orion's belt point towards Sirius. So I don't know if you can see my mouse, but if you follow the three stars and go down, the big bright star is Sirius. It's a beautiful star. It's worth viewing. Okay, so I'm going to move on to some of our photographic section members' images, but this time, rather than just show you images, I thought I'll put a bit of information about what they've actually imaged. This one was by Michael. It's an image of the Rosette Nebula. And I've just put a little bit of information there about it. Rosette Nebula is a vast emission nebula located 5,200 light years away. The star-forming region lies near a large molecular cloud in the constellation Moncaros, the Unicorn. It's closely associated with the young open star cluster NGC 2244, also known as the satellite cluster. NGC 224 appears in the center of the rosette. You can see the stars quite clearly in there. The hot young stars of the cluster were formed from the nebulous material in the last 5 million years. So they're quite young. Nice picture, Michael. The next one, again by Michael, is Thor's helmet. So this is an interesting nebula. It's in Canis Major. Again, we're near, it's just very close to Sirius, slightly to the east of Sirius. It's also known as Thor's helmet because it looks like a helmet with the two wings coming out the side and is meant to look similar to the Norse god's famous headwear. The nebula produced by a massive hot Wolf-Rayet star emitting a stream of charged particles as the stellar wind that expands out and produces an interstellar bubble. I will talk a little bit about Wolf-Rayet stars in a minute. Another picture by Michael. Michael's star on the show this time. This one is the Whirlpool Galaxy, M51. It's in Canis Venactici. I can never say that. Not without my teeth in. It's one of the best and most famous examples of a spiral galaxy that is presented face on to us. Indeed, probably only Messier 31, the great nebula of Andromeda, and that technically isn't completely face on its own angle, is a galaxy as popular and well known. So, so at the center of the Whirlpool Galaxy, there is a supermassive black hole, and it's the gravity from that supermassive black hole that's causing the two galaxies to interact with each other. There's NGC 5195, which is the orangey red looking galaxy, which is just above it, is interacting, and gravity is pulling material from stars basically from one to the other. They will eventually merge. This is one I took a week or so ago. Famous, massively imaged Horsehead Nebula by everybody. I was just trying out a new telescope, trying to get it right. Also, the Flame Nebula, which is the point to the left of the Horsehead. The both emission nebulas, and they're about between 900 and 1500 light years away. It's just below Orion's belt. So again, Thor's helmet. I've gone back to this because I want to talk about Wolf-Rayet stars. This image by Steve, another brilliant image of Wolf-Rayet of Thor's helmet again. I'll just start with a bit of information. The star associated with Thor's helmet is Catalogue WR7. The WR stands for Wolf-Rayet, and it's 280,000 times brighter than the sun and 16 times more massive. And this is located about 15,000 light years away in Canis Major. So what I've done there is just show a Hubble picture of it, which does it probably a bit more justice. But a bit of an explanation there for Wolf-Rayet stars. So, I mean, just to put it in context, our sun is 1.3 million times the volume of our Earth, and it's 330,000 times the mass of Earth, considering that's mainly hydrogen and helium. It gives you an idea of the sheer size. Our sun is 5,500 degrees C at the surface, but for our star is quite puny compared to these Wolf-Rayet stars. Wolf-Rayet stars are massive, bright stars. So I've got some numbers down here just to give you an idea just how big they are. They're over 20 times the mass of our sun, millions of times brighter, plus the temperatures start at and exceed 30,000 degrees C. And as to its size, it's difficult to determine this because it varies. They burn themselves up so quickly. They run out of fuel very quickly, and it's difficult to judge their sizes. They actually are tearing themselves apart. And also, the radiation driven from them is so strong, such a strong stellar wind, it's blowing out 10 million miles per hour. And that's why we get these beautiful nebulas appearing from them. The star sheds out 2,000 billion tons of material every year. That's like spitting out 3 Earths into space annually. So, that's quite an interesting. Fortunately, there's not an awful lot of those in our galaxy, but it's just interesting to know a little bit about these stars. So really, that does cover my talk. And if there's no questions, I'll hand back to Alan.
Okay, thank you very much indeed, Martin, for that fabulous talk there. And congratulations to the photographers for those wonderful pictures. It's hard to imagine those stars, those Wolf-Rayet stars, being so huge, so hot, marvelous, incredible things indeed. So again, thank you very much indeed, Martin, for that. I'm now going to pass you over to Dennis, who's going to introduce tonight's speaker. So over to you, Dennis.
Over to you, Dennis. Thank you very much. Apologies, we had a slight technical issue which had to be resolved first of all. And to all of you in the room, thank you for coming. It's obviously a very nasty night out there. So having made the journey here, we'd like to say thank you very much for coming. Just a couple of things to say. I noticed on the little run through there of people who are online, we've got a gentleman in New Mexico, Bob Burkett, and he did a talk for us a few months ago, which is on the YouTube service, if you'd like to look at it at some stage. So if you're listening, Bob, thank you very much, and I hope you're going to enjoy it. Now, we come to the main part of the evening, which is why you're all here. We have with us Cathie Clarke, and she's a professor of theoretical astrophysics at the Institute of Astronomy, Cambridge. Cathie studied at Cambridge and Oxford and was previously a research fellow at the University of California, Santa Cruz, lovely part of the world. Lecturer at Queen Mary University, and in 2016, Cathie was awarded the Eddington Medal for the Royal Astronomical Society for her work in developing the theory of photo-evaporation from protoplanetary disks. So a big warm welcome to Cathie Clarke.
Okay, well, good evening, everybody, and I echo the thanks for turning up on what wasn't a very nice night for driving, as I know, but it's great to see you. And also nice to be back. I know I wasn't in this venue, but I did speak to you back in 2017, and very much enjoyed the occasion. So I put together a talk about some things that I'm working on at the moment. So just to warn you in advance, I'm not going to come to very definite conclusions because it is work in progress, and that's the nature of scientific research, that you're always on a voyage of exploration. I am a theorist myself, but you'll probably be glad to know that I won't be showing you lots of equations during this talk. I'm the kind of theorist who likes to figure out what the theories mean in terms of reproducing and explaining the observations that come from telescopes. So we've already seen lots of beautiful images in the previous talk, and I'll be showing you lots of beautiful images as well. Like you, I admire them because they're beautiful, but also I try to learn as much as possible about what's actually happening to create these images, and the way that you do that is through a mixture of theory, sometimes using a pen and paper, but more often using a computer, and then trying to sort of simulate what the results of that theory would look like and compare with astronomical data. So the three topics I was going to talk about, the first one is extremely topical at the moment, which is trying to find evidence of young planets in disks. So really baby planets, planets that are about 1 million years old. We don't have many candidates at the moment, but it's a very interesting field. We heard a bit about winds just now in terms of Wolf-Rayet stars. Probably what's less well known to people is that there are also powerful winds that boil away protoplanetary disks, and it's probably this that blows away the material that would otherwise form more planets, and therefore it's all part of the history of our solar system, probably, that there was a strong wind blowing during those first few million years of the solar system's existence. So I'll talk about how one can find observational evidence for that. And then the last bit, which actually relates to some of those beautiful images we just saw about all the glorious clusters there are out there, including R136, that spectacular cluster in the Magellanic Cloud. A lot of star-forming environments are pretty different from the kind of solar neighborhood examples where we take a lot of our observations. And therefore, if we're interested in planet formation in general, although we're obviously going to start by studying the star-forming regions that are in our backyard, we also have to think that globally throughout the galaxy and throughout the universe, planet formation may be quite different, maybe more efficient, less efficient, we don't know, but we're just starting to scratch the surface of thinking about how environment affects planet formation. So just very quickly remind you why disks exist at all. It was actually figured out in the 18th century by the theoretician Laplace. He just worked out that if you have a rotating cloud of gas and it collapses down to form a star, it won't all go into the star. Centrifugal effects will tend to make the gas cloud flatten so that it can collapse one way parallel to the rotation axis of the cloud, but can't collapse at right angles to that. And so you go from a spherical cloud to collapse down into an object with a disk around that. And if you could actually just play the little video clip, this was a sort of simulation which was sort of state of the art at the time in the 1990s. One of my first graduate students did this calculation just showing the formation of a single disk around a star. You can see one is the sideways view showing how the centrifugal forces are stopping the material flowing in, and that's the plan view showing that you've created a disk, a couple of spiral arms there, and a star in the middle. And at the time, this was terribly exciting because it was the first time that anybody had ever been able to simulate the formation of a single star. This seems quite funny now because, decades on, people are simulating the formations of hundreds of stars and seeing how they interact with one another. But this was the sort of infancy of modeling star formation. But anyway, Laplace was right. He just did it by thinking about it in his study. But now computers demonstrate that you do expect stars to form disks as a natural byproduct of their formation. And the first really good observational evidence of this was these wonderful silhouette disks, which were discovered in the Orion Nebula cluster in the 1990s. They were actually a serendipitous discovery. They were studying the emission, the hot emitting gas in Orion, and they saw these sort of oval dark things, which are disks seen in silhouette against the bright background. And this caused a lot of excitement because people had already believed that disks should exist, but they'd never seen them. And there suddenly they were in Orion. They already thought they were there because they'd seen evidence from the spectrum, the amount of infrared light that young stars give out, that they probably did have disks, but it was just very gratifying to actually see them. But again, to show us how far we've gone, so that was in 1995, 2016, ALMA was commissioned, the Atacama Large Millimeter Array, and you see the progress as it's being made, the sort of images that you can get of a disk around a star. And I'll be telling you a bit about those images in a moment. This isn't an optical image being taken by ALMA. It's being taken in the region of the spectrum where the wavelength is about 1 millimeter, sort of microwave. And because the name ALMA will crop up quite a lot, I'll tell you a little bit about it. So it's located in the Atacama Desert, as the name suggests, and it's got very large antennae, which is good to make it sensitive. So they're sort of big light buckets, which are spread out across this plateau. They're spread out because the further apart you have the individual elements of an interferometer, a telescope array like this, the better the spatial resolution, which is why you saw that fantastic detail in the image that I just showed you. And the reason it's in the Atacama is famously very dry climate, and the Earth's atmosphere, in most places, especially Britain, has got a lot of water vapor in it, and water vapor absorbs strongly in the millimeter part of the spectrum. So you have to go to the driest place on Earth to have a good place for a millimeter observatory. And what ALMA is able to measure, it's particularly sensitive to cool dust. And when I say cool, I'm talking about a few tens of degrees above absolute 0. So like sort of minus 260 odd degrees centigrade. And the kind of dust which is emitting most efficiently at those kinds of wavelengths are dust grains which are about a millimeter in size. So we're really sort of detecting what you could regard it as sand almost. It's that kind of scale. That's not the only thing that ALMA can detect. It's also good at detecting carbon monoxide gas, because that produces emission from carbon monoxide molecules which are at the right wavelengths for ALMA to detect it. And why it's interesting to be able to use a molecular line is that you can measure its Doppler shift, and that can tell you something about the way that the gas is moving. If you look at the dust, that's not coming out at any particular frequency, so you can't measure the Doppler shift from it. So you can measure the intensity, you can look at structures, but you don't get any information on the motion. What is unfortunate is that you can't use ALMA to measure the hydrogen, and the universe is mostly hydrogen. So if you want to know how much does your disk weigh, you'd really like to be able to measure it in hydrogen, but unfortunately it doesn't have any transitions in that part of the spectrum. So we have to look at carbon monoxide instead, and then you have to worry about whether the carbon monoxide to hydrogen mass ratio is actually constant everywhere. So getting the masses of disks is a slightly dark art, because you have to fold in, as I say, the ratio between the carbon monoxide and the hydrogen. But mostly in this talk, we'll be talking about the dust in any case. So this is a famous montage of images taken in a study published late in 2018. It was, I think, the first large program on ALMA to look at protoplanetary disks. Remember, it was approved in 2016. I was on the panel that was sort of assessing what we should use the ALMA's time for. And this seemed very exciting to me at the time, because it was what's called a blind survey. They didn't sort of cherry pick what they thought were going to be the interesting objects. They just said, let's take a whole lot of young stars and just use ALMA and just stare at them and see what we see. And some people were saying, yeah, but there might not be anything interesting there. And the reply was, well, let's just have a look. We've got superb sensitivity, we've got superb resolution. Let's just see if they're all dull and boring. There is a risk there, but we might see a whole lot of structures. And as you see, it was a gamble that paid off, because most of these disks have got quite a lot of structure in them. And I'll also notice that although you've got the odd spiral, like the one IM loopy 3 from the left on the top row, on the whole, they're not spirals, they're rings, they're annular structures, a bit like Saturn's rings. And immediately the sort of conclusion that a lot of people sprung to, which probably is still the leading hypothesis, is that just as the rings in around Saturn are divided by dark grooves, which are created by Saturn's moons, this is a sort of scaled up version of this, and that where we see dark in this in these images, it's because the dust has been swept out by the motion of planets. So immediately is, can we actually use this, even though we can't see the planets directly, use images like this to figure out where the planets are? And maybe we can use these images to also, in some sense, weigh the planets and figure out whether we've got big planets or little planets. So that's the sort of great task at the moment, to try and figure that out. So the way you do that is all a matter of simulating stuff on a computer. So if you have a planet orbiting a star and you put in a gas disk around it, that gas disk is going to be affected. It's going to be perturbed by the presence of the planet, and it's going to create a kind of gap in the gas. The dust is entrained in the gas and is coupled to it by drag forces, so it doesn't behave exactly the same as the gas. And how closely it follows the gas depends on whether it's very small grains, which would follow the gas, or bigger grains, which might do something different. So the take home there is that how the dust responds is partly a question of how big the dust grains are, and we don't really know that from the beginning. But assume something about the dust grain size, calculate what this system, which is a dusty disk with planets in it, what is the emission produced by that, and then make a synthetic image, which is what this would look like if it was observed by ALMA. So you put exactly the same experimental configuration in terms of how many antennae were used and that sort of thing, to apply that to your model as you would do to if you were observing the real thing. And what you're doing then is changing things like the mass of the planet to try and figure out which of these models best matches the data. So we got very excited about all this sort of thing back in that's 2017. I'll say mainly myself and the people I work with, they're often theorists, but did have some very good observers in my group at the time. I'm very pleased to get some time with ALMA. This was actually before that montage of images came out, so we really weren't sure what to expect. We were interested in this young star called Ci Tau, so that's in the constellation of Taurus, where there are a number of young stars. And why we were particularly interested in Ci Tau is that it's the only star with a disk which has probably got a hot Jupiter orbiting it. A hot Jupiter is a planet which has been detected by the reflex motion of the star by its Doppler shift, and you can only detect that kind of Doppler reflex if you've got a planet which is really close to the star. So the hot Jupiters are hot because they're very close to the star. So before we trained ALMA on this source, it had been suggested that it had a hot Jupiter, but we didn't know whether it had other planets in it as well. And so that was the image that we got from this. As I say, it was before that montage of images you've just seen, so we were extremely excited when we saw this. The hot Jupiter itself would be down. If I had a pointer, I'd be able to just point into the sort of yellow spot in the middle of that image. You wouldn't be able to resolve it with ALMA. So that's one Jupiter mass planet, which is really close to the star. But then what we were observing were these grooves in the distribution. So we played the game that I was describing on the previous slide of simulating images with different mass planets, trying to find the ones that best matched the emission. And we decided in the end that we had weighed the planets in this system. So what this plot shows here, this is a diagram of all the exoplanets that have been discovered. So this is the distance from their host star along the bottom and the mass of them up there. And familiar things are that Venus is there, Earth is there, Uranus, Neptune, Saturn, Jupiter, etc. And this is just showing what we thought we have discovered in Ci Tau. Very rich ensemble of planets. You've got this one, which was known about before we did the ALMA observation. That's the hot Jupiter. So it's hot because it's very close to its star. It's also a massive planet. It's about 10 times the mass of Jupiter. And then we figured out from doing this modeling I was talking about that the other planets in the system were in this sort of area. So more or less sort of Saturn, between Saturn and Jupiter in mass, or slightly below Saturn in that case. So this was good. We had a press release about it at the time. It was a bit annoying in some ways that the beautiful graphic on the right, made by our graphic artist at the Institute of Astronomy, got far more attention than the actual image. We were much more excited about the actual image, but the graphic on the right, which is an illustration of what we found, obviously attracted people more. But what I wanted to say about doing that, and since then a number of people have done similar things on different disks, is that I mentioned it before, that figuring out the planet mass also depends on what you assume about the sizes of the dust grains. So there is some uncertainty that creeps into that part of the process. And then perhaps more seriously is that not everybody has agreed that those rings are created by planets at all. There are other theories for what could produce the rings involving instabilities in the disk. So although it's fun to figure out these planet masses, we'd really like to corroborate this by looking for planets and disks by some other method and putting it together. Now, the most obvious method, and it's a shame that it doesn't work in most systems, at least not at the moment, is to just go and image planets as they form. And this is this famous system, PDS-70, which about 5 years ago now detected a bright spot observed in scattered light. So this is a situation where you're looking in optical light at a star disk system, and you're seeing the light from the star, which is scattered off material around it. And the bright spot you see in the top image is a candidate protoplanet imaged directly. Remember, when what we were doing before, we didn't actually see the planet at all. We were just trying to infer it from the way it was disturbing the dust. But this is actually the brightness of a planet. And then even more excitingly, a couple of years ago, this is an ALMA observation. Another planet in that same system had a detection of material around it with ALMA, which looks like a circumplanetary disk. So the protoplanetary disk is the place where all the planets are orbiting, but the circumplanetary disk is the disk actually around the planet. So it's sometimes called the moon-forming disk. It's this idea that each planet as it forms has its own little disk. At the time, everybody thought, oh, well, let's go out and find lots of these, but there's only a very small number that have been detected. We're not quite sure why that is. What is very, very interesting about this particular system is that you can follow from year to year, start to track how this planet moves on the sky, because you can pinpoint it quite accurately. So that's really the kind of demonstration that it's not just a background galaxy or something like that, if it's actually doing a bit of an orbit around its star. So this is really exciting. This is really the way to go. But on the whole, it seems that the planets aren't really bright enough for us to be able to detect them. So we're back to indirect methods again, and this is just something that I'm working on at the moment, which is why I'm mentioning it, is that another thing that planets do, as well as carving out gaps, is to produce spiral patterns in their disks. This is demonstrated in these simulations there. So none of this has anything to do with anything that's ever been seen. This is all the results of doing a computer simulation where you put your planet in the disk, you work out the emission that's produced by it, and you see that's that there. So you can see that you've got a bit of a gap and a spiral, and then you mock observe it with ALMA, and you can still see a bit of a spiral there, and that's for putting in a Jupiter mass planet at about 50 AU from the star. And it's interestingly enough, although in the raw simulation, and you see the density distribution there. It looks so the gap is the most obvious thing. By the time you've done all the processing on it, probably the most conspicuous thing in this image should be the spiral. Now, why I think spirals are interesting compared with gaps, compared with rings. Two reasons. They're more unique. If you see something like that, it probably can't be created by anything other than a planet. And the other thing is that even if you can't see the planet itself, the spiral pattern should be rotating on the sky in lockstep with the planet. So that would allow you to sort of corroborate that it is a planet spiral if you could measure the rotation of it on the sky. So it would be very interesting to detect something like that. But just to show you that it's sensitive to quite low mass planets, this is an interesting simulation because here what's been done is putting in just a Saturn mass planet in that disk and doing a Mach-Balmer image, and you'd just look at that and you'd say, well, I don't see a spiral in that. Well, I certainly don't see a spiral in that. But if you then analyze it, and every radius in that image, you take the average going round through 360 degrees, and then take the actual value at a particular point and take away the average, that's what's called the residual map. So it's just showing you like the sort of variation at every point as you go round in a circle compared with the average for that circle. And in that residual map, even for something which looks totally invisible to the naked eye, there you start to see the spiral. So we're starting to think, well, some of these disks which seem quite featureless, if we analyze them in this way, we should be able to pull out the spirals, even though our eye wouldn't pick that out. And so this is work which is in progress. Here's Ed, one of my master's students, who's working on this, and I hoped he'd be able to produce a plot for me to show you this evening, but hasn't quite got the code working yet. But what I've set him to do is to say, well, a lot of disks don't show spirals, so that must tell you something about the planets that are around them. They can't be too big or you would see the spirals. So can you generate lots of sort of fake observations and then say from that what kind of planets you could have in disks compared with what's ruled out by the observations? And I think that's just a very sort of typical way that scientists behave. You know, everybody thinks it's all about discovering something, and of course it's really interesting when you do discover something. But sometimes when you can't see something in an image, that also contains information. And this is what we're doing. We're looking at all these null results and saying, well, it's still telling us something about the planets that are not there, and that in itself is kind of informative. So that's where we got to on that, and I'm sorry we don't have results, but it's a work in progress. Now let me tell you about winds. This is moving on to my second theme. This is an artist's impression of all the sort of busy stuff that's going on in the gas and dust around a star as it forms. And I want you to focus on the sort of later stages. It's sort of going along the top and then ending up in the final thing when the dust and gas has been dispersed and you've got your planetary system down there. And somehow you have to get from the disk, form planets in it, and then get rid of the dust and gas. And one of the prime candidates for getting rid of that dust and gas is blowing a wind off the disk. Show you a bit of evidence of why we think that the dust and gas has to be blown away rather suddenly. And that's a plot here of the amount of dust that you see around young stars, depending on their age. So everything below about 10 million years is what I'd call a protoplanetary disk, and we see it in dust, and it's got hundreds of Earth masses of dust in it. And everything that's older than that is what's called a debris disk. And as you see on this, it maybe doesn't look like a huge decline in the amount of dust, but this is a logarithmic scale, so the amount of dust suddenly goes down at about 10 million years or so by a factor of 10 to 100 or something like that. And it's because of this that I first started developing these ideas about the fact that it was a wind that was blowing the disk away. Now, what do I mean by a wind? The sort of wind that's blowing in a night like this is, as you know, the result of there being pressure variations in the atmosphere. So you get bulk motion of the Earth's atmosphere moving from regions of high pressure to low pressure. And it may be that the wind that's blowing off disks is exactly the same sort of effect, that it's going from high pressure to low pressure. But the conditions are very, very different. These are hot winds. These are at about 10,000 degrees. The material that's coming off is hot and ionized. And you might say, well, I thought you were telling me that these disks were only a few tens of degrees above absolute zero. Well, why is it 10,000 degrees? And what we think is happening is that there's energetic X-ray and ultraviolet radiation from the star that it's orbiting, which is heating up the surface of the disk and literally sort of boiling it away, and a wind coming away from there. And what I've been interested in the last 20 years is developing the theory of these winds and then asking the question, well, can we actually see observational evidence for them? Because that's what, in the end, is going to be interesting. So the ingredients are, first of all, you need a theory. And as I say, I won't go into that, but we have the model that I developed a few years ago for how hot the wind is, how fast it's going, and the shape of the flow. By the way, how fast it's going, it's fairly puny compared with the Wolf-Rayet wind that we heard about a few minutes ago. They're traveling at about 10 kilometers a second, which is about 30,000 kilometers an hour. So it's pretty fast by terrestrial standards, but nowhere near the millions of miles an hour we were hearing about for the Wolf-Rayet winds. And I said they were ionized. That means that the hydrogen's had all its electrons, each hydrogen atom has had its electron pulled off. So we don't get any information about emission lines from hydrogen because it's just too hot. They're just atoms and electrons whizzing around. So we have to go to another kind of element if we want to look at the spectrum, the line spectrum coming from these winds. And it turns out, sounds rather exotic, but actually the best tracer of these winds is actually neon, which is obviously quite a rare element in the universe. But at these kind of temperatures, it's still got plenty of electrons left. It hasn't all been ionized like the hydrogen because it's got many more electrons than hydrogen's one. And so you get emission lines produced by neon. Now, why are we so interested in looking for emission lines? It comes back to this business about the Doppler shift, that if my hand is a disk and the wind is blowing off it, then you, the observers, would see blue shifted emission because it's coming towards you. You wouldn't be able to see the wind traveling away from you because it's blocked by the disk, but you'd see blue shifted emission. So the best, I like to say, the smoking gun of the fact that these winds are there is contained in this image here. And it's an image in the sense it's not really an image, it's a spectrum, it's a line. If the material wasn't moving, it would be centered on 0. And the fact that it's offset as a blue shift of 10 kilometers a second is telling you that yes, there is material that's boiling off this disk at 10 kilometers a second, which is what is expected. Now, the problem with this, this comes from a model of a wind, and this is showing you that most of the neon is coming from this kind of region. This is 10 astronomical units from the star. That's less than 1/10 of an arc second if you look at a nearby star-forming region. So what we can't do at the moment, or at least we haven't been able to very recently, is actually spatially resolved it. So when I say, yes, this is a smoking gun of the wind, we see this spectral line, yes, it matches. You're taking all this spatial information from this image and saying we can't resolve it at all, but it's gathering the light up and getting a single emission line out of that. It would be much more informative in mapping the wind if we could measure the spectrum sort of pixel by pixel, if you like, all over this image. That has not been possible until James Webb went up. And we are very lucky to get time in the first round of allocations of time on James Webb to do exactly this, to look at a star where we think there's a disk wind blowing off it. As I say, we have the models, and what James Webb can do is to tell you about the spectrum and how blue shifted or red shifted it is at different positions on the sky. This is the MIRI instrument on JWST. So very exciting. I've got a very good graduate student called Andrew, and he worked all the time that the data was being acquired, which was last autumn, on generating predictions of what it should look like when observed by MIRI. So a bit of the same process I was talking about before. You take your model, you mock observe it, and then you put in all this kind of image processing artifacts that you know would affect the real JWST data to make it look as much as possible like something would look like if observed with JWST. And the way that our team is divided is that we're working on the theory in Cambridge, and our observational colleagues are in Arizona reducing the data. And we have telecons about every month or so, in which we just sort of show each other images of where we've got to, both on the simulations and on the observations. And last telecon I went to, they both looked like kind of fuzzy blobs. So that was sort of good news in the sense that they looked broadly similar, but we're far from actually being able to say, yes, this really clinches the theory. We've got another telecon on this next week. So as I say, for somebody who's a theorist, it's always quite exciting when you get to the point of comparing it with the real data. We think that even JWST, which has got superb resolution compared with any spectrograph that's ever been used in the near infrared before, we think it might be too tough to actually be able to resolve very much, but we shall see. But in the meantime, quite recently, I realized that there was possibly a much easier way of finding winds from disks. And this is another montage of disk images. The white contours are the emission from ALMA, but they look quite different from what you saw before, because all these disks have been selected to be edge on to the observer. So obviously on the sky, they're randomly oriented, some are face on, some are edge on, but this is a sample of special edge on disks. One of the things you see from that, I just think about the ALMA data, which are the white contours here, is that if you look at something very edge on, like the one on the top left, it's extremely thin. And that means that those sort of sand-like grains I was talking about have really settled down to a thin layer. That's the place where the planets are actually forming. There's a very thin layer then. So what's all this coloured stuff above and below? Well, that's actually imaged in the optical by the Hubble Space Telescope, and it's scattered light again. It's light from the star, which is scattering off dust particles, just in the same way that you get the scattering in the Earth's atmosphere, and is then deflecting the light so that wherever there's dust, you see that signature of scattered light. And I think you can see that there are quite a few disks in which you see a kind of hourglass structure above and below the disk. And this is really just qualitatively, first of all, what you'd expect if you've got winds blowing off the disk. They've got little dust particles in them, and they get entrained, and then they scatter the light. So since I went to a conference, probably the first conference I went to since COVID, actually, I went to a conference in France a few weeks ago. We started working on this, and it's very hopeful, actually. We think we'll be able to constrain how much material is leaving these disks by how bright these hourglass shapes are. So again, it's a question of work in progress, but in the end, relatively low resolution data like this, because the sort of scales we're looking at here are hundreds of astronomical units rather than what we're trying to get at with the NEON and the JWST. This may be the way to go for characterizing winds, but again, work in progress. And then the final topic, well, as I said, relates to the issue of how typical are the kind of disks that I've been showing you images of so far. As I said, they're all taken in our kind of solar neighborhood backyard, all the sort of familiar star-forming regions like Taurus, Ophiuchus, Lupus, etc. They're all pretty close, maybe sort of 50 to 100 light years away. And I have to explain what this plot involves. By the way, I've got another Andrew's picture up there. He was a former PhD student who's worked with me a lot, both when he was in Cambridge and subsequently on this whole issue of environmental effects on planet formation. So what you want to be thinking about with this plot is that the vertical axis tells you what is the value of the ultraviolet field, radiation field, which is bathing your disks. So if I'm in the middle of something like the Orion Nebula Cluster, this is the Orion Nebula Cluster here, I've got really bright O stars, lots of ultraviolet, and so disks which are high, or regions which are high in this plot, have got a strong ultraviolet environment, whereas what's plotted along the horizontal axis is how dense is the star-forming region. For example, the core of the Orion Nebula Cluster is maybe 1,000 times denser than the Taurus star-forming region. So dense clusters are here, this way. Highly irradiated clusters are there. These lines here are just plotting out different parts of the cluster. Like near the center is always densest and most irradiated, so they start up on the top right, and then as you go further out, it goes below. So here are the kind of regions that are close to the sun, and which of course we study because we get the best resolution because they're close by, and we can, because they're brighter because they're close by. So it's obvious that they're the ones that will get the best information. But what I'm saying from this plot is they're really not very typical, because they are not as dense as most regions, and certainly very low in their ultraviolet background fields compared with other regions. And what it comes down to is that if you're in a region where you've got O stars, and I've got some pictures there of the Arches cluster and the galactic center, for example, or MGC 3603 up there. These are regions which are very popular. They're big clusters or associations, and they've got lots of O stars, and that means lots of ultraviolet radiation. So the question is, if these regions these environments are quite different, does this matter in terms of how planets form and evolve? I think one of the best bits of evidence is from a study that I was involved in the Cygnus OB Association. So it's not a dense cluster, but it's got a lot of OB stars, so bright stars. And tell you what this colourful plot is doing. It's saying, well, I know where the bright stars are, so I know which parts of the cluster I'd expect to have very strong ultraviolet fields, which I've colour-coded blue, so they're quite close to where the bright stars are. And then I can have a colour code of different colours here, going from blue to brown to green, etc., as I get into regions where the field should be lower and lower. And then for each of those regions, I can say what fractions of the stars in those regions have disks. And that's what I've plotted up here. So this is how much ultraviolet they have. So the highest ultraviolet is the blue region. And then this is the fraction that has disks. It's pretty conclusive there that the stronger the ultraviolet field, the lower the fraction that has disks. And we think this is actually a kind of scaled up version of the disk wind that I was telling you about before. But now it's not being driven by the ultraviolet from the stars that it's orbiting. It's being driven by the ultraviolet of having massive stars really close by. So overall, we think that disks will live less long and be fried and boiled away quicker if they form in dense clusters. And therefore, ultimately, when we start thinking about Drake's equation and the probability that that life happens, it may actually be less likely, but we don't yet know how much less likely for systems which form in regions with lots of O stars around, just because the disks get fried possibly too fast for you to have time to form planets. So that was talking about the environmental influences in terms of ultraviolet radiation. The last thing I want to talk about is the effect of stellar density, because remember that was the other thing that was on that plot. There's a lovely picture of 47 Tuc, a beautiful globular cluster, very dense in the center, again 10,000 times denser than the solar neighborhood down in the center there. And this was showing off the capabilities of Hubble Space Telescope, showing that what with old telescopes looked like a sort of amorphous ball of stars and a globular cluster. When Hubble came along, you could start to separate the stars out really cleanly and measure properly the densities inside these clusters. So what effect does that have on planetary systems? What it turns out is that the main effect isn't so much what happens when they're very young while there's still a disk around the stars, but more that if you then live in a cluster like this over its entire age, and these globular clusters are very old, they're about 10 billion years old. So supposing we just formed an ordinary planetary system in 47 Tuc, those planets would then have to live in an environment where they were being jostled by the other stars in the cluster for 10 billion years, which is a long time, even by astronomical standards. And what we did, so this was a study with Andrew, this picture I showed you before, was to figure out, first of all, a model for how this cluster, what its dynamics are, how many stars there are, how fast they're moving. Then in our model, put little planetary systems in there and then watch as they get jostled and then see how many are destroyed. And what we found was that, supposing I give all the stars in this cluster when they were born a Jupiter at the radius that Jupiter orbits the Earth, so at 5 AU, and I put it in a cluster like this, what happens to Jupiter? A couple of things can happen. One thing is it can just get stripped off because it gets enough energy by being jiggled by the other stars around it gravitationally that it flies away. But more interestingly, sometimes it goes the other way and ends up being perturbed inwards, so it ends up as a hot Jupiter, so really close to the star. So start them all at 5 astronomical units like Jupiter. Some get ripped off, but some end up as hot Jupiter systems. Now, why this is interesting is that 47 Tuc could be a kind of template for what star formation was like in our galaxy a very long time ago. As I say, it's about 10 billion years old. It's quite a different environment from what we have today. It's very low in metallicity. It hasn't got many heavy elements because it's much closer to the start of the universe. It would be fascinating to know, does 47 Tuc have planets in it? But there's no way, given the distance of 47 Tuc, that we'll ever be able to image a Jupiter sitting at the orbital radius of Jupiter. At 5 AU, you can't do that. It's just far too close. But if you form a hot Jupiter, then there's another way of detecting it, which does work in principle in 47 Tuc, and that's the transit method. And you probably know that the Kepler satellite has found lots and lots of planets through the transit method, just looking for the little dips in the light as a hot Jupiter, as a hot Jupiter or a hot Neptune, whatever crosses the disk of the star. So in a way, it's kind of good news if we are interested in finding planets in 47 Tuc, that we believe that ones that were formed at larger radius should get shaken down and end up as hot Jupiters, because there we've got a chance of catching them. Now, there was a study done about 20 years ago by Hubble Space Telescope that looked for these transits in 47 Tuc. It didn't find any, but according to our models, it shouldn't have found any. But it just shows it's one of those questions that it's worth revisiting now that we've done the calculations, do another survey. And then in the end, we hope to actually put constraints on whether planets can form in very low metallicity environments like 47 Tuc. So again, a point where I don't have a a conclusion in telling you that planets didn't form then, but I think we're sort of setting out the framework that we have to use to figure out whether they do. So just to wrap up, as I've kept emphasizing, all this is sort of ongoing work. ALMA's got a lot of structure in its images, and it's probably telling us about planets, or at least we think it is, but we have to do more to quantify that. I'm quite excited about the wind stuff and the fact that we've got potentially some ways to measure that. But I think this is something which we're really just starting to try and figure out the very different implications ultimately for life in the universe, but even just for forming planets and letting them survive. If we go to more exotic environments where you have to worry about ultraviolet radiation and high stellar densities. So again, very much work in progress. So with that, I'll leave it, and thanks for your attention.
Well, there's a fascinating look into the amount of research that's actually going on. In fact, there was so much there, I kept thinking, where does it all end?
Absolutely.
So are there any questions from the audience here tonight? One brave person.
Just wanted to check something I heard when you were talking about the density of the cluster.
Yeah.
If I got it right, you said 10,000 times our local space now.
Yeah.
So if my mental arithmetic's right, we're talking stars that are light hours apart, not light years. Am I right? My math's just rubbish.
I don't think it's quite light hours. I used to have that calculation at my fingertips when I gave this talk. Yeah, because locally we're about 0.5 stars per cubic parsec, and in the sensitive globular clusters we're talking about 10,000 stars per cubic parsec, so that is about 20,000 times. But it means that your average distance to your nearest star is about a cube root of.
I'll cube out then.
I think you're a cube out. So, but I mean, the night sky would be pretty interesting if you were there for that reason. But no, not light hours, I don't think.
Thank you very much. Thank you, Cathie. Okay. So thank you very much for that. And I think I'm going to pass myself back to Alan, correct?
Well, thank you very much indeed, Cathie. What a terrific talk that was. There's so much exciting stuff going on there. Incredible, the modelling and testing and seeing what could be, well, discovered in the future. I think we've actually had a question just arrive in. So before I start the end speeches, we've got a question from Jeff Bryant. What would be the next step in astronomical instruments that would allow better data for your studies? So I don't know if you can answer that one, Cathie.
Okay, so I don't know if you guys online can hear me. Am I seeing thumbs up there? Yeah. So I think that there are a number of things. One is this combination of spectral and spatial resolution, which you get from the JWST, for example. That is really key, because you need information both on how things are on the sky and also how fast they're moving. So that's important. And the other thing is to be able to have an instrument like ALMA that can go out to longer wavelengths, get out to centimeter wavelengths, where you can start to detect larger bodies than the kind of sand which you're detecting through ALMA. So I think for my kind of studies, both of those would be extremely important. Thanks for the question.
Thank you very much indeed for that, Cathie. We couldn't see you, but we could certainly hear you nice and clearly. Okay, so I'll repeat my thanks to Cathie for coming all the way down in such atrocious weather. We are very, very grateful that you made it, and we hope that you have a safe journey home. So thanks from all of us at the Hertford Astronomy Group. So now, just a few messages for the rest of you. Quite important ones, so I'd like you if you could just stay on for a couple of minutes more. I won't make it very long. As you probably gathered, Jerry hasn't been well. He's not here this evening. and I'm sure that we all wish him a speedy recovery. We're still planning to do the My Telescope Doesn't Work session on March the 25th at the Bramfield Village Hall. Details of that are on the website, and also were in the last newsletter. So if you want to get some advice on telescopes, perhaps you'd like to make a booking for that one. Shortly after that, there's another meeting, which I'm sure you're going to find interesting. On the 29th of March, the Institute of Physics have got a talk in the adjacent lecture theatre, teaching computers to study the stars. I think that's going to be quite relevant to what you've heard this evening. This Dr. Ashley Spindler is giving the talk, so if you'd like to come along to that, please book your tickets through Diane Cran, and again, links are on the website for that. We've got a little bit of a problem with our next meeting on April the 12th. Gordon Rogers was due to come along and talk to us about the sky at night with a laugh. However, I had a message yesterday that he's been offered a date for an operation that he's been waiting for a long time, and of course he would like to take up that offer. I did say to him that I think with the current NHS system they'll probably cancel it anyway, but I don't think we can count on that. So at the moment we are looking for another speaker for April the 12th. When we get details, of course, we'll pop that onto the website, and if any of you who are watching this want to volunteer to give a talk, please get in touch with me rather quickly. That brings us to the last item. In the last newsletter we sent out, we actually put a little question right near the end to say that we're planning, obviously, next year's talks as well to continue from these, and we'd like to ask you, are there any subjects you would like us to find speakers to talk about? It's yours, all of our club, and if there's some subject you think, yeah, that would be a good one, I'd like to hear about that, then give us the challenge of finding somebody to speak about it. So that just about concludes the meeting for today. I would like to say thank you again to Cathie for giving the talk, to Martin for having presented the sky at night, for the tech team. We got Dan and Steve who are really getting to grips with this, and many thanks for all their hard work there. And a special thank you to Dennis for being the host this evening. So to all of you at the university, I hope you have a safe journey home, and we look forward to seeing you again. Those of you on Zoom, if you want to stay around and have a little bit of a chat, by all means do, but I'll stop the recording here and officially say good night, see you next time.